So let's review some basic data structures. First, we'll do a quick review of the concept of collections, and then we'll talk specifically about lists. So collections. A collection is just a bunch of values or objects. So in programming languages like Java, typically they're of a common type. So we could have a collection of integers or a collection of strings, or a collection of food objects if we're creating some sort of game or simulation that has the concept of food. Usually collections can be extended, and what I mean by that is that we can add more items to them. So this is a little bit different than arrays that we've seen so far. So arrays in Java have a fixed size when they're created. We can't add new items, add new positions into the array, but we can create a new array and replace the original one with a newer, larger one. So just kind of conceptually, you just can think of a collection as just kind of a big bunch of data with no particular structure or order to it. Most types of collections have additional properties that either require some sort of ordering or some sort of access pattern for getting data and adding data to the collection. So we'll review that in a minute when we look at our first major collection, the list. Collections typically have certain common operations. So one of the operations that they usually have is some form of enumeration or going through all of the items in the collection. They typically allow people to identify the number of items that are currently in the collection. There's usually a way to add an item. There's usually a way to remove a specific item, and you can also usually find a particular item. Sometimes find is even more specific, like finding a maximum or minimum value. But the concept of max and min actually require that the data have a total ordering, so that imposes some restrictions on the data type in the collection. Okay, so collections can be represented as an abstract data type, where certain methods represent these common operations. So for example, size could be a size method that returns an integer. The add method takes an item to add in and maybe has a void return value, but adds the item to the collection. Maybe a remove operation is given a particular item. It removes the first occurrence of that item if it exists, and returns true if an item was removed and false if it wasn't. Maybe a find method finds a particular item and returns it, and returns null if the item can't be found. Okay, so let's look at our first collection, the list. So a list is actually a collection of items in a particular order. That doesn't mean that the items are sorted or in order based on their values. It means that somehow the items in the list are in an order. One of them could be considered first, one could be considered second, one could be considered third, and so on through the last item. So this idea of first, second, third kind of leads to the concept of indices. So oftentimes lists allow access by index. So let's go ahead and take a look at Java's list interface. So Java uses the concept of interface types to represent abstract data types. So Java's list is a typical example of lists. Lists exist in lots of different programming languages, but oftentimes they support very similar sorts of operations. Usually when people want to use a list, they're concerned about accessing things by some concept similar to index, first, second, third, fourth. Okay, so let's take a quick look at Java's list interface. Okay, so this is the Java list interface. So interfaces define methods that are available. So again, it's about a kind of a pure abstract data type. It describes the operations that should exist and how they should work, but it doesn't actually provide any code that will do these operations. So let's look at a couple of key operations. So there are a couple of methods called add. One of them is just given some some element data, and it appends to the end of the list. Another one is given two parameters, two arguments, an index, an integer, and an element to add. And it will insert the specified element at the specified position. If the position isn't valid, you encounter an error. Okay, so these two methods are about adding things to the list. Kind of the complement of that is the get method that's provided an index, and it will return an item at that index if there is one. If the index is invalid, it'll throw an exception. which is very similar to what an array would do too if you tried to access an invalid index. There's an isEmpty that will return true if the list is empty and false otherwise. There is a contains that will check to see if a given object is in the list and return true if it is and false otherwise. Okay, so that's a sampling of common list operations. Probably the most important ones are adding things and accessing a particular index. There is also remove. In fact, the Java's list has two different forms of remove. You can remove something at a particular index, or you can remove a particular object. Okay, so now let's consider the concept of implementation. So for any particular collection, there may be different implementations. So by implementation, I mean a different way of achieving the same sort of behavior of doing the same operation. So for lists, we'll consider two different ways to handle lists. Using arrays, very similar to what we saw in Module 1 Studio, and using a linked structure. And these are really, really common choices when implementing data structures. Oftentimes you have to consider what happens if you use array-based storage versus linked storage. This doesn't apply to all data structures, but it does apply to many of the ones we'll be looking at in this unit. Okay, so first of all, let's consider the array-based implementation. So we'll consider managing an array. So basically we'll consider a class that has an array as a property. And in fact, in addition to having the array, we will somehow want to track the size of the array. In Java, we've got the implicit .length property on our arrays to keep track of the overall size or capacity of the array. We saw in Module 1 Studio that sometimes there's a benefit to having a bigger array than you strictly need. There are performance gains when you're adding on to the end repeatedly. So we may want to add in another notion, the idea of a value that will, variable that will keep track of the number of things currently in the array. So in my next example, I'm going to refer to that with the variable n. Okay, and we'll also use the array doubling strategy that was used in the Studio, so n will not always be equal to the length. Okay, so now we'll go through an example of managing an array, and we'll go through a sequence of several different operations and look how Java's array list might behave. So we'll think of our array list as containing three different variables. One of them will be the array. And the array has a .length property to it, so we'll keep track of that as well. And finally, we'll have a variable n that keeps track of the amount of data that's actually in our array. We'll use the array doubling strategy that we saw in Module 1. Okay, so I'm going to keep track of these three different ideas on a piece of paper. So I am going to represent the array with kind of a little box diagram, and I'm initially going to start off with an empty array. So I'll draw a weird little square, and it will have a corresponding length of 0, and my n, the amount of data I currently have in the array, is 0. And I'm basically just going to use this little table, and as I update these variables, I'll just cross out the old value and replace them with their new and improved value. So the first thing we'll do is we'll do an add operation. We'll add the number 12 to this array. Okay, so initially my array had a length of 0 and was empty, and my n was 0. We're going to add a 12. So I'll check and I'll see my capacity is 0, but I also have 0 things in my array. But if my capacity is 0, I'm going to have to make a newer, bigger array. So we'll start off with an array of size 1, and it'll be able to hold a single item at index 0. So its length is now 1. So we've essentially replaced our old array with size 0 with a new array of size 1. We have to put the number 12 in this array, so we'll put it at the first available spot. And now we've got one item in our array. So this is after we added 12. And remember, the add method merely appends to the end. Okay, so our second operation is an add of 16. So I look at my capacity, which is 1. I can hold one thing. Oh, and I've already got one thing in it, n is 1. So I'm out of space. I'm going to use my array doubling strategy. So I'll make a newer, bigger array that can hold a total of 2 things. We'll go ahead and copy the data over from our old array. And our new array has a capacity of 2. And I'm now done with the old array. Okay, so we will need to append our new item, our 16, at the first available index. Currently, the n tells us how many items are in our array, and it will always be the index of the first available space, which is kind of convenient. So we'll insert our new value, 16, at index 1. We now have a total of 2 items in there after we did our add of 16. Okay, let's do another operation. Oh, this operation is a little bit more complicated. So this is the add at a specific index, and our index is 0. So basically this is like inserting an item here. We're still adding something, so we'll have more items in our array list when we're done. Okay, before I can do anything, I have to see if I actually have space. So I'm going to go ahead and check, and we've got a capacity of 2. We've got 2 things in here. We definitely can't add something. So the first thing I'm going to do is I'm going to go ahead and grow my array. So I'll go ahead and double its capacity yet again. So we'll have a total capacity of 4 now. I'll copy over my old data, my 12 and my 16, into indices 0 and 1. And our total capacity is now 4. And I'm done with my old array. Okay, now I'm going to go ahead and do the insert operation. Now I could have somehow combined this together with copying data over, but I chose to split it into 2 separate parts. So now that I've got capacity, I'm going to actually go ahead and insert my new item at index 0. So I'll go ahead and insert it at index 0, and I somehow need to move every item from index 0 onward forward 1 spot. So I'm going to go ahead and start doing that. I'm going to move the 16 over to index 2, and then I'll move the 12 over to index 1. And then I'll go ahead and insert my 14 at index 0. Okay, and now I've got one more item. I've got a total of 3 things in my array. Okay, at this point, I still have capacity for one more item. If I wanted to do another append and add on to the end of this, I already have space and I wouldn't need to create a new array. Oh, but that's not our next operation. Our next operation is a remove operation. So the remove, we'll have to somehow go out and find if the item's here. And remove, if you remember, finds the first particular copy of an item. In this case, we'd start at the beginning and maybe look until we find a 16. We've only got one 16 in here. Now, there are different ways we could handle this. If these were objects, we would probably replace it with a null. Since they're integers, we would maybe replace them with a 0, or we could even actually just ignore it. We could just change our value of n to indicate that now we just have 2 items, and if we have to add something new, it would be added at that first unused box. As I'm working on paper, I'm actually going to literally remove it. In code, we may not be able to do that, or we might have to replace it with a special value like 0 or the maximum positive or negative integer. There are a couple of different options. Okay, so the basic process here that we've gone through allows us to do some kind of accounting and figure out how our 3 different variables are managed and how different operations will impact those 3 different variables. Okay, so this is the basics of how the array list works. An array is managed. There's separate notions of the capacity versus the amount of data that's actually in it. Our different methods use these 3 different concepts to figure out how to operate. Okay, so let's go ahead and do an implementation of a linked list as well, and this will be a doubly linked list. So we'll create a node object. So a node object is going to contain 3 different things. It'll contain a place to store data, and it'll contain links to its neighbors. So we're doing a doubly linked list, so that means that each node contains 2 links. One to the predecessor, which we'll refer to as the previous, and one to the successor, which we'll refer to as the next. Okay, the class itself is going to contain 2 links, one to the head of the list, the front node in the list, and the other to the tail of the list. So I'm going to use a particular notation for my list. I am going to draw nodes as circles. And I'm going to divide the circle into 3 different pieces. The middle spot is going to be where I store the data. The top spot is going to be the reference to the next item. The bottom spot is going to be the reference to the previous item. So next will typically look like some sort of an arrow that connects us up to the next thing. Prev will be an arrow that connects us up to the previous thing. In our case, we're working with numbers, so we'll assume that the data is just a number, like the number 1, for instance. In some cases, the next or the previous may need to be null if there's nothing after us, the last item in the list, or nothing before us for the first item in the list. In that case, I'll draw arrows with a little X on the end to indicate that it's a dead end, that it doesn't go anywhere. Okay, we also need to keep track of the head and tail of our overall list. So I will use a little variable for that. I'll use head towards the left of my diagram and tail towards the right of my diagram. So let's begin with our operations. So initially we'll have our head variable. That's going to be a dead end. There's nothing in our list just yet. And the tail will also be a dead end because there's nothing in our list yet. We'll do the exact same operations that we've already done. So we'll add the number 12 to our list. We'll have to create a node that contains the number 12. Since there's nothing in our list yet, its next and its previous are both empty. We will update the reference to the head of our list and also the reference to the tail of our list, so they now both refer to the single node. Okay, now let's add a 16. Just like before, we will create a new node. We'll put 16 in that node. Okay, now we need to somehow patch it into our list. So we know it belongs at the end of our list. So we can use the tail to go to what's currently at the end of our list. We can access its next pointer and update it to connect it to our 16. And of course our 16's next should be null. We also know that wherever the tail points used to be the end of our list, and the 16's previous node will be what used to be the end of our list. So we'll take whatever our tail is currently referring to, the 12, and we'll make the 16 point to it as well. And finally, since we're doing an add, we're adding on to the end of our list, we'll have to update our tail to be this new thing that we've just appended on to the end of our list. Okay, let's do our next operation. Our next operation is the add that's going to add at index 0 the number 14. Okay, to add by index, we probably need to start at the beginning of our list and iterate through our list until we find the index that we're looking for. In this case, it's basically telling us that we need to go the first step, the 0th step away from head. So just like before, we'll go ahead and create a new node. I'm going to go ahead and draw it in here right a bit above where the head is at. And we know in this case that it has to refer to what used to be at index 0, the number 12. So the head currently points to that, so we'll go ahead make the next pointer revert to 12. We'll go ahead and make the previous pointer be empty, and we'll put the number 14 in here. And of course, since we've added at index 0, that changes the head of our list. So the head of our list now refers to this 14. We also have to update the next thing from the 14 needs to have its previous updated to be the 14. So we'll update that as well. Okay, so there are a couple of different things that are going on here. Every time we insert a node, we need to think about how it's going to impact the nodes around it. Will their next be updated? Will their previous be updated? We also need to think about its impact on the head or the tail. There are some pretty concrete rules for how to handle this in all possible situations, but it requires just a little bit of thought and reflection. Okay, let's move on to our last operation. So we're going to remove the 16 from the list. So we will go through the list. We have to find the 16 first of all. So we'll start at the head and we'll check each node. 14, nope, that's not a 16, so we'll follow its next pointer. That gets us to 12. That's not 16, so we'll follow its next pointer. That gets us to this node, which is 16. So this is the one we want to remove. So we'll start working on the remove process from here. We need to see if we've got anything after us. We don't. If there was something after us, we'd have to update its previous to somehow skip past 16. But in this case, there's nothing after it. Okay, so now we need to worry about what's before us. Whatever is before us now needs to skip past the 16. So in this case, there's nothing past the 16, so we have to follow this from the 16 back to our previous node. We need to change its next to be null. Okay, and again, we also have to think about not only the impact of our neighbor's previous to next, but also the impact on the tails. This is removing the last item in the list. So the tail now needs to move to the previous item. Okay, and at this point, the 16 is completely unlinked. I'm going to go ahead and erase it from my diagram here. Java would do a process called garbage collection, and if there's nothing that refers to an object, it will automatically get rid of it for us eventually. Okay, and so with that, we've gone through 3 adds and 1 remove. Okay, another type of ADT is a queue. A queue is like a line, so if you think of a line at a bank or a ticket window or something where people queue up, get in line one after the other. And just like at a bank or a ticket window, it's first in, first out, otherwise known as first come, first serve. So the term first in, first out is commonly used in computing, and it has the acronym FIFO. Okay, so queue operations, it has some, as an abstract data type, it has a couple of common operations. One of them is enqueue, where you enqueue an element, which is basically adding an element to the back of the line. There's also the complement of that, the dequeue, which removes an element from the front of the line and returns it. There's an isEmpty method to determine whether the list is, the queue is empty or not. So let's go through a conceptual example. Let's enqueue the number 5, and I'm going to show this as though it's an array, although queues can be implemented in different ways. So this would put a 5 at the front of the line, and then enqueuing a 10, we'll put a 10 in the second position behind the 5. And then enqueuing a 12, we'll put a 12 at the third position behind the 5 and the 10. And then a dequeue operation will remove and return what's at the front of the queue. So it'll remove the 5 and return it. And that'll leave the 10 and the 12 in the queue with 10 at the front of the queue. Then enqueuing a 1, we'll add the 1 onto the end of the queue. So it'll be 10, 12, and then 1. And then doing another dequeue, we'll again remove the thing at the front of the queue, the 10, and return it, leaving just the 12 and the 1 in the queue with 12 at the front. A stack is another common simple data structure. So a stack is like a stack of plates on the spring at a buffet, where the plate on top was the last one to be put on that stack. Another common example of a stack is a Pez dispenser, which is a dispenser for a particular brand of candy. So the Pez dispenser looks something like this. This comes from WikiHow. So the Pez dispenser slides open and the candy is put in, and the last piece of candy is at the top of the stack. And the way it dispenses candy is by pushing back on the head at the top of the Pez dispenser, and the last piece of candy, the one towards the top, is the first one to come out. Okay, a stack is a last in, first out data structure, LIFO. The last thing that goes in is the first thing that comes out. So again, if you think of the stack of plates at a buffet line, the last plate that ended up on the stack is the first one that comes out as someone's going through the line, and the Pez dispenser, the last piece of candy to go into the Pez dispenser, is the first one that come back out. Just like lists, stacks have operations defined on them. So there's the push operation, which adds a new item to the top of the stack. There's the pop operation, the complement of the push, that removes and returns the item on the top of the stack. And just like a queue, there's an isEmpty operation that returns true if the stack is empty. Okay, so let's go through a conceptual example. Let's imagine that we push 5 onto a stack. So in this case, I'm going to show a stack somewhat like an array, but again, it doesn't have to be implemented with an array. And then we push a 10 onto the stack. So in this case, a 10 would be the second thing on the stack. It's currently at the top. And then pushing a 12, put the 12 on the top of the stack. So the bottom of the stack is 5, then 10, then 12. And then we'll pop data off of the stack. So this will remove and return the thing at the top of the stack, the 12, leaving behind the 5 at the bottom and then the 10. Then if we push a 1 onto the stack, a 1 goes on to the first available spot above the 10. And then if we pop, the 1 is removed again. So again, the last thing that was put on the 1 is the first thing that gets removed. LIFO is the acronym, last in, first out. Okay, stacks, queues, and lists are some of the most fundamental simple data structures. And stacks and queues can actually be implemented by using lists. So the choice of implementation has a huge impact on performance. So both a linked list and an array-based list could be used to implement either a stack or a queue. And these have an impact on the performance. The choice of what you consider to be the front or the top of either the stack, the queue or the stack also has an impact on overall performance. So spend some time thinking about how these different implementations of a list could impact the in queue and dequeue of a queue and the push and pop of a stack.